All right, here we go. So part 2, we know the value of this integral, but we also know that we can break it up as the integral over the x-axis. It's still f of z dz, but we're going to switch it to f of x dx because on the x-axis z is just x. And then we have the integral over f of z of the actual arc on the circle. And so our goal, of course, is to show that this guy goes to 0. So let's write that down. So we need to show that this integral over the circle gamma of r of f of z dz goes to 0 as r goes to infinity. Okay, so how does one go about doing that? Well, we're going to use the tricks that we learned at the beginning of this lecture to bound our function, and then we're going to realize that, hey, we're living on the circle of radius r, and so things actually work out quite nicely. So here we go. Let's do a little bit of analysis. So f of z is the modulus of f of z is going to be the modulus of z squared over the modulus of z to the 4th plus 1. Why don't you go ahead and pause this and see what you can do with the inequalities. Hopefully you see right away that you can pull that out, and then the bottom you can say is less than or equal to the modulus of z to the 4th minus 1, absolute value of all of that. All right, and now you realize, wait a minute, I'm living on the circle. Let's say on the circle gamma of r, the modulus of z is just r. So this guy is actually equal to what? R squared over the absolute value of r to the 4th minus 1. We can safely assume that r is bigger than 1, so we're going to go ahead and delete the absolute values now. And we get r squared over r to the 4th minus 1. And so here we go. This is really good. We're almost done. Let's copy this integral, and we're going to put it right here. And we're going to say, okay, let's put a so, and then we'll put a colon, and we're going to bound it. And we know from our theorem that the modulus of this integral is less than or equal to the length of the arc. The length of the arc, think with me, this a full circle of radius r has circumference 2 pi r. We're doing half of that, so pi r. So the length of gamma is pi r times our bound of f on gamma, r squared over r to the 4th minus 1. Now we can write this as what? Pi r cubed over r to the 4th minus 1. I want to be very clear in everything, so I'm going to go ahead and rewrite this as pi over what? R minus 1 over r cubed. As r shoots off to infinity, what happens? This part goes to 0. So you've got the form pi over infinity minus 0. This whole thing is going to 0. This guy goes to 0 as r shoots off to infinity. We've done what we set out to do. So we're actually almost done. So we can say, okay, so thus, think about it. If the modulus of this thing is going to 0, if it's on its way to 0 as r goes to infinity, right, it's less than or equal to this expression, and this expression is going to 0. That means this is going to 0. But the modulus of z is 0 if and only if z is 0. So we can conclude then that the integral of f of z dz along gamma of r, the whole integral, is going to 0 as r goes to infinity. And now we've got what we want. So let's write down the full statement. So we've seen that pi over root 2, this is the value of our function f of z dz around the closed contour C. And this is equal to minus r over r of f of x dx. Sorry, the integral from minus r to r of f of x dx plus the integral over gamma of r of f of z dz. And then we've seen that, okay, think about it. Let's let r run to infinity, and this value doesn't change. This integral doesn't change. The size of the arc, it doesn't matter whether the arc looks like this or whether it looks like this. Nothing changes. It's a closed contour, and you're not gaining any more residues. So this doesn't change regardless of the size of r. So if we let r shoot off to infinity, we can conclude that pi over root 2 is the limit as r goes to infinity of these two pieces. Let's just copy them Whoops, did not want to do that. Let's, I think we can paste them still though. It's the limit as r goes to infinity of, yeah, this guy. Okay, we can break the limit up over the sum, and so we get pi over root 2 is the principal value. We need to be careful. If I just wrote minus infinity to infinity down, I would not be quite telling the truth. It's the principal value of the integral from minus infinity to infinity of f of x dx plus 0, because this part goes to 0. And so finally we can say, okay, I've got the principal value, so I'm going to try to say everything here that we can. Minus infinity to infinity, the principal value of this f of x dx. This is what? The principal value of what was our function? X squared, I forgot it now. X squared over x to the 4th plus 1 minus infinity to infinity dx. This guy is exactly pi over root 2. But we know that that's equal to the improper integral from minus infinity to infinity of x squared over x to the 4th plus 1. So the moral of the story is, the full moral is that this improper integral of a real valued function is equal to pi over root 2. Oh, and by the way, in case you care, the integral from 0 to infinity of x squared over x to the 4th plus 1 dx. I forgot a dx somewhere along the game. Let's go back and catch all of those. I think I got them all. This is equal to 1/2 times pi over root 2. So pi over 2 root 2 as well. So that's it. We're done for the semester. Great job. It's been a blast. There are not very many courses that I would have liked to have taught online as an extra thing this fall, but you guys and this material have certainly been worth it and have been a lot of fun. So thank you for your work, and I'll be in touch with you about what we're going to do for a final.